while we were away, we were working on some of the homework problems. If you guys are having struggling with the homework problems, stop by, see me, uh, and we can get those things ironed out. If we have any time left, we'll show a few of them here, but we want to make sure we get to the materials at hand. So you guys will probably have a little homework time at the end. So what we're going to do now is jump up to chapter 19 and do the second portion of what we're discussing. It continues. Let's just think about this for a minute. You guys saw reactions that happened, and every one of the reactions when you dissolved all the 6 chemicals in the lab, every one of the chemicals dissolved. I don't think anybody disagrees with that. You didn't have to do anything. All you had to do was mix them together. All the 6 chemicals dissolved. We call that a spontaneous reaction. A spontaneous reaction is one that occurs without you doing anything. So just a quick review of the materials from chapter 5. Remember, at constant pressure that the enthalpy change equals the heat transferred between the system and the surroundings. So delta H equals the enthalpy of basically the products minus the enthalpy of the reactants, and that's going to equal Q. As long as we're at constant pressure, then that's just MC delta T. Okay? Now, thermodynamics is different than thermochemistry. All we cared about was the energy change. Well, there's another energy change that occurs, and that energy change that is accompanied by a change in what we call order or disorder. Now, what you think order and disorder means is going to be a little bit different in chemistry than what if you think about cleaning your room, or if you think about a bunch of people running out of a burning building, or something like that, or you got a whole bunch of Legos that you turn into a nice Darth Vader head or something. What's a spontaneous process? A spontaneous process that ones that occur with outside intervention. You absolutely did not have to do anything when you dumped the 2 chemicals together. When the water and the chemical met, they dissolved, right? Now you're going to say, well, wait a minute, I had to stir it. If actually you didn't have to stir it. If you'd have waited enough weeks in a sealed container, that stuff would have dissolved itself. You just helped it speed up the process a little bit. So the first law of thermodynamics says that, if you'll remember back from chapter 5, we said that energy is always conserved. So in a spontaneous process, it's going to be one that's going to occur without any outside intervention. For example, if I leave my bicycle out long enough, it's going to rust. It may take it 30 years, it may take it 50 years. But if I leave my bicycle out long enough, it will rust. That is a spontaneous process. About 8 chapters from now, we'll do a chapter on the speed of a reaction. We do not care today about the speed. All we care today is, does it happen without outside intervention? If it does, it's spontaneous. It may take it 3,000 years to happen, but I didn't have to do anything. It's going to happen. As opposed to a reaction that, for example, I could put water in this room every day, all day long, and you will never see the water split into hydrogen and oxygen without outside intervention. You have to run electricity through it in the presence of a catalyst if you want water to separate into hydrogen and oxygen. It can be done. Matter of fact, the first person that figures out how to do it is going to be the richest person in the world, because we'll have all the free fuel we ever need. Pure hydrogen, pure oxygen. But you can't do it without outside intervention. And guess what that outside intervention is? A whole bunch of energy added. So in that case, that's not good, is what we're saying. That's not good. So if you'll remember back, we said that the change in a system's internal energy is its heat transferred and the work done on the system. So just reviewing, if Q is what, the system releases heat. Sign. The system releases heat if the sign is negative. Very good. And if the system absorbs heat, then the Q sign is positive. You absolutely positively have to know that yesterday. You cannot not know that. You can't have any hesitation in your answer about that at this point. If you do, you're a week, 2 weeks behind already on this unit. That's an absolute. If W is blank, the system did work on the surroundings. Positive. If W is blank, the system had work done on it. Negative, right? So those are backwards. Okay? If the system does work on the surroundings, then that's negative. If the system has work done on it, then that's positive. So those are the 4 signs as we go there. Remember, all this is from the system's point of view. We said that unless you're a chemical engineer, all these signs are always opposite. But that's what you're in. You're in chemical engineering in here right now. So all those signs are correct for this course. All right? What's the matter? Nothing up there is incorrect. Everything's from the system's point of view. All those are correct. The system does work. It's negative work. If the system has work done on it, it's positive work. If the system loses energy, that's negative. Think of the system losing energy. So the system has to lose energy to do work. The system has to release heat. It has to give away some of its energy. Both these are both giveaways. Yeah. Okay, now, a reversible process. Technically, here's the quickie way to define it. Undo exactly what you did and you got what you started with. It's another way to say reversible. Okay? So both the system and the surroundings go back to their original state. For example, a change of state is a classic example of a reversible system. If you have ice at 0 and water at 0, you can add a certain amount of heat called the heat of fusion, and you can melt all the ice and turn it into water, and it'll still stay at 0. If the water gives away the exact amount of heat as this took in, it'll turn right back into the ice. You can go right back and forth between ice and water. Boom, 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 boom. It is a completely reversible process. So that is considered a reversible process. You got it? That's considered reversible. Now technically, all reactions are reversible, just some of them are really hard to reverse. Okay, if you have the right ingredients, you're probably never going to, for example, you would never be able to burn some butane and take the CO2 in the water and turn it back into butane. Now, somebody out there might be able to do that by a certain process, but I'm going to tell you right now, there ain't anybody going to make butane that way. That's nature's way of doing it. So, irreversible process is to get back to what you started with. It requires more than just an undo. And, that's sadly, if you restore it to the original system, then the surroundings have to change. Okay? So, classic example is you can turn hydrogen and oxygen into water. It is considered a spontaneous process. But I'll tell you right now, to split that water back into hydrogen and oxygen, you will have to change the surroundings in order to do that. And that's why we don't do it routinely. So, for example, I'm going to give you a real easy example. If a gas expands into an evacuated space, here's piston, here's a vacuum, here's gas. Let's pull the piston back. Maybe. There we go. We just lifted it up. So now that gas expanded into this space, right? That is a spontaneous process. If you let some gas out in this room that stinks, Won't we all smell it eventually in this room? We will, won't we? Now, what are you going to have to do to get that gas trapped back into the bottle again? It's not just easily reversible, is it? You're going to have to do some work to get it back in there. So watch, you're going to have to push the piston back in, slide the thing back down, and now it'll be back to its original state. But what did I have to do? When I lifted that out, let's go back. When I lifted this out of here, that spontaneously happened on its own. That filled up, right? But to get it back to its original state, I'm going to have to do work on the system. Boom. Then drop that plug back in there, and now I've got it back to the original state. So you notice the difference? The stuff expanded to fill the tube on its own, but I had to do work on the system to get it to go back to the original state. So which way was reversible? Oh, excuse me. Which way was spontaneous? First one, right? Which one's not spontaneous? The second. Okay? So, please note, there's about 4 statements that need to be made here because we're going to run out of time on this video. Whenever a chemical system is in equilibrium, now we have not discussed and talked about equilibrium, you can go reversibly between the reactants and the products. Technically, in a spontaneous process, the path between the reactants and products is considered to be irreversible. Thermodynamics talks about the direction of the reaction, not its speed. And look at number 4. In general, exothermic reactions are more likely to be spontaneous. Nature likes losing energy, not gaining it. Nature, most reactions that are spontaneous are exothermic. Most of you in your groups had reactions that went up in temperature. Some of you were the lucky winners that yours went down. But by far, I'm not trying to give away the whole game, but 4 of the 6 reactions were exothermic. One of them was almost isothermic, which means no energy change occurred. All right? Processes in which the system's disorder increases tend to occur spontaneously. New statement. Disorder is capital S and called entropy. Delta S is the final state minus the initial state. If delta S is positive, the products are more disordered than the reactants. If delta S is negative, the products are more ordered than the reactants. Large entropy means a large number of microstates. I'll talk about what that is in the next section. Very disordered. Watch this picture, because I'm running out of time here. See my 2 pictures? You see the disordered room and the wrecked up cars? Those are very disordered. Small entropy, there'll be small number of microstates, that'll be less disordered. Watch the room and watch the cars. Nice rows of cars and a nice clean sewing room here. Do you see them? So we say that the second pictures that you see have less disorder than the first set. There's fewer microstates. What the heck's that mean for chemistry? It's easy to talk about it in terms of a room and cars lined up, isn't it? It's a lot more difficult to talk about it in terms of chemicals. All right? And you can pause this slide to take those notes because I'm going to run out of time, so I'm going to go ahead and run this. So entropy at the particle level. There are 3 types of motion, each having kinetic energy. It looks like I'm going to have to start this anyway. There's translational, vibrational, and rotational. So I'm going to show you these, but I'm going to have to do it in the next video.